Welcome to Copilot Podcasts. Two circular wire loops floating in space, carrying electrical current, positioned at completely random angles to each other. How do you calculate the exact force and torque between them? It sounds simple, but this problem has been stumping engineers for decades. Today, we're diving into groundbreaking research from the International Journal of Mechanical Sciences that just solved this puzzle using something called the Kalantarov Zeitlin method. You'll understand why this matters for everything from wireless charging to magnetic levitation, and how mathematicians are giving engineers powerful new tools to design the impossible. Let me hand this over to someone who can actually explain what's happening here without making our brains hurt.
So imagine you have two circular wire loops. Think of them like invisible donuts made of wire, each carrying electrical current. When current flows through wire, it creates a magnetic field. And when you have two magnetic fields interacting, they create forces.
Right, like how two magnets either attract or repel each other.
Exactly, but here's where it gets tricky. If these wire loops are perfectly aligned, like two rings stacked on top of each other, the math is manageable. But what if one loop is tilted at a weird angle? What if they're offset from each other? What if one is rotated?
Oh, wow. So it's like trying to predict how two invisible magnets will push and pull each other when they're floating in zero gravity and spinning at weird angles.
That's a perfect analogy. And this isn't just academic curiosity. According to the page content, these calculations are crucial for electromagnetic levitation, wireless power transfer, medical devices, nuclear magnetic resonance, and even robotics.
Wait, so when my phone charges wirelessly, someone had to solve this exact problem?
Absolutely. The page content specifically mentions wireless power transfer as one of the key applications. When you place your phone on a charging pad, there are coils in both devices, and engineers need to calculate the optimal positioning and force interactions.
That's incredible. So what makes this new approach special?
Well, the traditional method that engineers have been using is called Grover's formula, developed way back in 1944. It works, but it's computationally intensive. The Kalantarov Zeitlin method is actually from a 1986 Russian textbook on inductance calculations. It's been hiding in plain sight for decades.
So someone just dusted off an old Russian math book and revolutionized electromagnetic engineering?
Not quite that simple, but close. The researcher Poletkin from Karlsruhe Institute of Technology adapted this method specifically for calculating forces and torques between arbitrarily oriented circular filaments. The page content shows he derived new formulas presented in analytical form through integral expressions.
Okay, you're going to have to break down integral expressions for those of us who haven't touched calculus since college.
Think of it like a recipe. Instead of saying, add some flour, an integral expression gives you the exact mathematical steps to calculate something complex. In this case, the kernel function is expressed in terms of elliptic integrals of the first and second kinds.
Elliptic integrals sound terrifying.
They're just mathematical tools for dealing with curved shapes and complex geometries. The beautiful thing about this research is that it provides an alternative to Babič's expressions using elliptic integrals, giving engineers multiple mathematical pathways to solve the same electromagnetic problem.
So it's like having multiple routes to the same destination?
Perfect analogy. And according to the page content, all derived formulas were programmed using MATLAB language and are available as supplementary materials, so engineers can actually use these tools immediately.
That's pretty generous of the researchers. But how do we know these new formulas actually work?
This is where the research gets really impressive. The page content shows they validated their new formulas through comparison with a series of reference examples. But here's the kicker. They also derived additional expressions by differentiating Grover's formula for mutual inductance.
So they basically created a mathematical cross-check system?
Exactly. The validation process involved comparing results across 3 different mathematical methods. It's like having 3 different calculators all arriving at the same answer. That gives engineers incredible confidence in the results.
Let's talk about real-world impact. The page content mentions electromagnetic levitation. Are we talking about floating trains here?
Magnetic levitation is definitely one application, but the page content also mentions superconducting levitation, micro-machined contactless suspensions, and biomedical applications. Think about MRI machines, where precise magnetic field calculations are crucial for image quality.
Wait, so this research could improve medical imaging?
Absolutely. The page content specifically lists nuclear magnetic resonance as one of the applications. When you're designing MRI coils, you need to know exactly how they'll interact magnetically to get clear, accurate images.
That's fascinating. What about the wireless power transfer angle? How big of a deal is that?
Huge. The page content mentions this applies to wireless power transfer systems, and we're seeing explosive growth in that field. Electric vehicle charging, smartphone charging, even powering implantable medical devices, all of these rely on precise electromagnetic calculations.
Implantable medical devices? That sounds incredibly precise.
It has to be. When you're powering a pacemaker or insulin pump wirelessly, you need to know exactly how much power you're transferring and where the forces are acting. Too little power and the device fails. Too much and you could damage tissue.
So this isn't just about making calculations easier, it's about making them more accurate for life-critical applications.
Precisely. And the page content shows this research covers all possible arrangements between two circular filaments. That's important because real-world applications rarely involve perfectly aligned coils.
Right, because in the real world, things are messy and imperfect.
Exactly. The research addresses what they call arbitrarily oriented circular filaments, meaning the coils can be positioned at any angle, any distance, any orientation relative to each other. That's the real world.
Let's talk about the validation process a bit more. How thorough was it?
According to the page content, they validated through comparison with reference examples from Babič et al.'s work and by comparing with results calculated using expressions derived from Grover's formula. They tested multiple scenarios with different coil arrangements.
So they basically stress tested their math against established methods?
That's right. And the page content mentions they obtained additional expressions for calculation of force and torque by means of differentiation of Grover's formula. This allowed them to verify their new formulas comprehensively and independently.
It sounds like they really wanted to make sure they got this right.
When you're dealing with applications like medical devices and electromagnetic levitation, you can't afford to be wrong. The mathematical rigor here is impressive. They're giving engineers tools they can trust for critical applications.
What's the broader significance here? Are we looking at a fundamental shift in how electromagnetic problems are solved?
I think we're looking at the democratization of complex electromagnetic calculations. The page content emphasizes that analytical methods allow you to obtain results in the form of a final formula with a finite number of input parameters, which can significantly reduce computation effort.
So instead of needing supercomputers, engineers can solve these problems more efficiently?
Exactly. The page content notes that while numerical methods in commercial software provide accurate solutions, analytical methods facilitate mathematical analysis, especially when you need derivatives for optimization or force evaluation.
That sounds like it could accelerate innovation in electromagnetic design.
Absolutely. When engineers can quickly test different configurations and optimize designs mathematically rather than through trial and error, it opens up possibilities for more sophisticated electromagnetic systems.
Looking ahead, what kind of applications might we see that weren't possible before?
The page content mentions applications in mechatronics, robotics, and topology optimization. I think we'll see more precise wireless power systems, better electromagnetic actuators, and maybe even new approaches to contactless manipulation in manufacturing.
Contactless manipulation sounds like science fiction.
It's already happening in some specialized applications. The page content mentions electromagnetic actuation and micro-machined contactless suspensions. With better mathematical tools, these technologies could become more widespread and precise.
So, when you step back from all the complex mathematics, what this really comes down to is giving engineers the tools to design electromagnetic systems that were previously too complicated to calculate accurately.
That's exactly right. And the beauty of this research is that it provides multiple pathways to the same solution. Engineers can choose the method that works best for their specific application, whether that's the new Kalantarov Zeitlin approach or the validated Grover derivatives.
It's like having a Swiss Army knife for electromagnetic calculations.
Perfect analogy. And with the MATLAB implementations available as supplementary materials, engineers can start using these tools immediately. That's going to accelerate innovation across all the applications we've discussed.
Here's what's remarkable about this research. It takes a 1986 Russian mathematical method and transforms it into practical tools for 21st century engineering challenges. From wireless charging to medical devices to magnetic levitation, engineers now have multiple validated approaches to solve problems that were previously computational nightmares. The next time your phone charges wirelessly or you get an MRI scan, remember that behind those everyday miracles are incredibly sophisticated mathematical calculations. And thanks to research like this, those calculations are becoming more accurate, more efficient, and more accessible to the engineers designing our electromagnetic future. Thanks for joining us on Copilot Podcasts. Sometimes the most profound innovations come from dusting off old mathematical tools and applying them in completely new ways.